concentration of the intrinsic carriers. Then we take ln. ln means natural logarithm. I think you know, at least at this level, you know how to use the natural logs. And then you multiply with a constant here. This constant, we call it Boltzmann constant. T is absolute temperature, and E is the electronic charge. Now this we can take them to be a constant which we call thermal voltage. So KT over E is known as thermal voltage, and we represent it with the letter V subscript T. So if we want to determine the barrier potential, we will do this. Let me ask Okoth. Okoth, you can see this equation?
Yeah.
Okay. So tell me, what is V subscript T? What do we call that? Mentioned it. It's known as
thermal voltage.
Thermal voltage.
Yeah.
So in this example, look at, Okoth, can you read example 4.4?
Determine the thermal voltage at 300 kelvins.
Determine the thermal voltage at 300 Kelvin. So we are not being asked in this example 4.4 to determine the barrier potential. We are being asked to determine the thermal voltage. And we see the thermal voltage, how we determine it. It is equal to Boltzmann constant multiplied by the temperature, the absolute temperature, and we divide by the electronic charge. We know, Okoth, what is the value of electronic charge?
1.6 times 10 raised to power negative 19.
Yes, good. 1.6 times 10 raised to power negative 19 coulomb. And the T we are given, Okoth, what is the value of T we are given?
300.
300. And we also, in an examination situation, you will be provided even with this constant, the Boltzmann constant. Its value is 8.62 times 10 raised to power negative 5 electron volt per coulomb. So we substitute that value from Boltzmann constant, we substitute T, which is 300, we substitute Q, which is also the one we are calling here, we substitute it as 1.6 times 10 raised to power negative 19. When we work out this one, which you can check, because it is also in those notes which I gave you, you will find it comes to 26 times 10 raised to power negative 3/4. Now this one, we can take negative 10 raised to power negative 3 is 1,000th. So we can say the thermal voltage can also be quoted as 26 millivolts. 26 millivolts. Okoth, do you understand how we are doing this?
Yeah.
Yeah, I will keep on referring to you because when I'm doing a presentation, I cannot see the names of the other students. So this question has been answered. Determine the thermal voltage at 300 Kelvin. Now, in the next example 4.5, maybe let me check whether I can get another student to take us through that. Let me ask Kimaru Mark. Do you hear me, Kimaru?
Yes, I hear you.
Just you are in a noise place. Please mute yourself. Mark, mute yourself. Oma Atieno, can you hear me? Ouma Atieno.
Yes, I can hear you.
I don't know. Okay, can you read example 4.5?
I can't see clearly.
Can you see the screen? Okoth, you can see the screen?
Yeah.
Please just read 4.5.
Okay. Calculate the building potential barrier of silicon PN junction at temperature 300 Kelvin. Depth at Na is equal to 10 per 16 cubic centimeter in the P region. The ND is equal to 10 per 17 centimeter cubic in the N region. Check Ni to be 1.10 cubic centimeter for silicon at room temperature.
Now I think, Okoth, the way you have read, now do it. What is this? What you are calling Na? What is Na? Okoth, what is Na? Now we have been talking about this. Na is what we call acceptor concentration. So you are given the acceptor concentration, and that's where we get the ores in the region. The acceptor concentration is 10 raised to power 16 per centimeter cubed. The way you are reading, you are saying centimeter cubed. This one, when you see the negative, it means per. So the acceptor concentration is 10 raised to power 16 per centimeter cubed in the end region, and the donor concentration is 10 raised to power 17 per cubic centimeter. Now, Ni is what called the intrinsic concentration. The intrinsic carrier concentration, 1.5 times 10 raised to power 10 per centimeter cubed. And this is for silicon. If you have another material, the intrinsic concentration will be different. So we look at equation 4.6, which is this one. This equation you can see here. When I substitute what we are given, and of course, if you remember in 4.4, we had determined the thermal voltage, is it? We just done it here. We got 26 times 10 raised to power negative 3/4.
Yeah.
So we come and substitute. We know VT, or the thermal voltage, is 26 times 10 raised to power negative 3/4. Now that is the value which we take at room temperature, and room temperature is this one in Kelvin, 300 Kelvin. Then we are given the acceptor concentration is 10 raised to power 16. The donor concentration is 10 raised to power 17. And the intrinsic concentration is 1.5 times 10 raised to power 10. Then we square it. You should not forget the squaring. That gives you 0.75 volts. 0.75 volts. So we are saying the barrier potential for a PN junction, which is meant from silicon, will be 0.75 volts. So we have illustrated how you use this equation, which was obtained as illustrated in the notes which I gave you. According to you, share with your classmates those notes?
Okay, yeah, I shared them.
So when I said here it can be shown, I showed it correctly. But mostly for you, you may not be asked to derive, but you can be asked to you can be asked to use this equation. I want to show you how your examination looks like. Just a minute, you will see. Now see, this is how your examination looks like. I want to show you what we are in that area. Doesn't seem to be there. There is no question. Now I think what we have done in this exam, we did not test that. We test that. But now look, the exam, you can be asked very simple things like what is the maximum number of electrons in the M shell of an atom? We score 1 mark. Then Roman 3, an intrinsic semiconductor has some ores in it at room temperature. What causes the production of these ores? I'm just showing you to be able to engage yourself. If you were in that exam, could you have answered that question? Now, a very simple one. What are the majority carriers in a P-type semiconductor? Now, explain how an N-type semiconductor is produced. But of course, you are given some information there. You are having arsenic atoms are added to pure germanium. Given that the atomic number of arsenic is at 3, obtain the electronic configuration of arsenic. Then also use the same information to explain how an N-type semiconductor is produced. Differentiate between drift and diffusion as applied to a PN junction. Now, the mistake some students make when they get this kind of a question, you are not being asked for drift current. You are just asked to explain what does drift mean, what does diffusion mean. Again, I'm showing you that you gauge yourself. Are you able to answer these kind of questions? So let's go back to our discussion. Now look at this homework. Okoth, can you read the questions given in this slide? Okoth, please.
Okay, this formula is used when calculating barrier potential. Define each term in this formula.
Okay, which formula? This one, the one which is given here.
All right. All right.
Yeah, so you are given, this is the homework questions. You are given this formula, then you are being asked, define each term. So this is an easy question. You know what K is, what T is, what E is. You also know what VT is. Of course, what is VT? Sino ulikuwa unasoma in here. You are the one who was telling us VT is this.
Yeah.
What is VT?
Thermal voltage.
What is E?
Electron charge.
What is T?
Temperature.
What is K?
Boltzmann constant.
Okay, good. Now read question B.
K has 2 values. Depending on the units used, set the 2 values.
Now we said this Boltzmann constant, if you check back what we did earlier on, when we introduced the Boltzmann constant, we gave it two values. One of them is 8.62 times 10 raised to power negative 5 electron volts per Kelvin. The other one, find out what it is. Can you read part B?
Okay.
Not B, C, please. C. Yes.
I can't see the V subscript clearly.
Now, what can I do to make it better? You cannot, yes, you are using a phone or a laptop.
Laptop.
Now you can see?
Yeah.
Okay, read.
Calculate the...
What do we call this one? We call this one barrier potential.
Okay. Calculate the barrier potential for a gas.
No, this is not gas. This is a compound, gallium arsenide.
Okay, gallium arsenide PN junction at temperature 300 Kelvin. Doped at acceptor concentration is equals to 10 to power 16 per centimeter cubed in the P region, and donor concentration is equals to 10 raised to power 17 per centimeter cubed in the N region. Take the intrinsic concentration to be 1.80 times 10 per 6 per centimeter cubed for gallium arsenide at room temperature.
Now you can see the intrinsic concentration of carriers in gallium arsenide is 1.8 times 10 raised to power 6. Now, if you see the one now which we gave for silicon, it was 1.5 times 10 raised to power 10 in the previous example which we did. So this is the homework, and in the notes which I gave you, this homework is there. Please do it. Okay. So look, for silicon, it was this one. For gallium arsenide is 1.8, 10 raised to power 6. This is 10 raised to power 10. I hope the others are following. And I want to ask you, please be taking your classes in a quiet place, not so noisy. You cannot concentrate. Now, the cut which we did yesterday was deliberately meant simple to ensure that nobody fails. Now, cut 2 will not be that simple, okay? So if you did not au kujiokolea kwa cut 1, there are some people who have done extremely well in cut 1. And the others who did not do very well, I was surprised. So please, you need to, you will see when you get your papers. So let's go back to our discussion. We can go to something else.